Okay, so let's take a look at a sample problem. So here it says that EMF and resistance in the circuit of the figure A have the following values: E1, E2, R1, R2, and capital R. What are the current I in the circuit? Okay, so here we have, this is E1, this is E2, and this is R1, R2, and capital R. So for R1, R2, R, they are just in series, so nothing special. We just need to add them together, so nothing special. And let's see, and also here, when you see this E1 and E2, they are actually connected in opposite direction, which means that this side is plus, this side is minus, and this side is plus, this side is minus. So you need to determine whether this E1 and E2 are added together or subtract each other. So here, when you consider the current I in this direction, so you need to consider the sign of the E1, E2 carefully. So of course it is like I equals the total E over the total R, something like that. So but we need to determine whether E1 and E2 are positive or negative. For resistance, it is very safe. You just add all the numbers together, it will be fine. So here I will be in the denominator. It is nothing but R1 plus R2 plus capital R. So nothing special because they are just in series, and all the resistance are positive value. So just add them together. For E1, E2, you need to consider direction carefully. So here we assume that I is clockwise. And then here, when you see for E1, I of course pointing upward, and then here negative and positive. So we will consider E1 will be a positive value, and then for E2 here, okay, if I is clockwise, so here I should be pointing downward, and then here the arrow pointing this direction. This is negative, this is positive. So you see, this is the arrow. Okay, so it should be a minus sign. So this is how you can determine whether it's positive or negative. So this is the arrow, and then you see this sign is positive. So E1 is positive. This sign, the arrow here, this is negative. So negative E2. Okay, so here we have 4.4 minus 2.1 over 2.3 plus 1.8 plus 5.5. So the final value should be okay, so this should be 0.240 ampere. Okay, for part B, it asks you what is the potential difference between the terminal of the battery 1, 2. Okay, it means that this point and this point, because in the green box here, it means the battery 1. It is a practical battery with internal resistance. So when it asks you what is the potential difference between the terminal of battery 1, so it asks you the potential difference between this point and this point. Okay, so for this whole wire, it should share the same potential, which means this is still point A. This is still point A, this is still point B. Okay, so here, for E1 it is 4.4 volt, 4.4 volt. Okay, and then here I is in this direction. I is in this direction. And when we consider 4.4, it means that this is higher, this is lower. This is higher, this is lower. And here I is pointing this side. So in that case, VAB, which means that it is something like VA minus VB, should be this part. This part is 4.4, which is E1, and then it should subtract I times R1. I times R1. Because when you consider the Ohm's law, it is something like, this is I, this is R, and then the V should be, this is higher than, this point is higher than that point. So we should have V equals IR. Okay, so you need to be careful about the sign of all the variable. So if this is a resistor, and then the current is from top to bottom, and then V, this is positive, the top node is positive, this is negative, then V equals IR. If it is the other way around, if it is like we define V is something like this, okay, with the same direction as the I. So here we should have V equals negative IR rather than that one. But usually you try to make it union that you only use this one. Okay, for the resistor, I points to this side, and then this node has a higher potential than the bottom node. So in this case, I is pointing upward. So this is positive, this is negative. So in that case, when you consider the potential difference from A to B, so this is positive, this is negative. This is negative. So we should subtract IR1. So in that case, we have 4.4 minus, this one is 0.24. 0.24 multiply R1 is 2.3. So this is 3.8 volt. Okay, so here we also talk about the junction rule, which we know as the Kirchhoff current law, KCL. KCL, not the KCL in the chemistry class, not the potassium chloride. Okay, so this is a Kirchhoff current law. So it means that the sum of the current entering any junction must be equal to the sum of the current leaving the junction. So I suppose we have known it in chapter 26. At that time we already know that. But here we would use it frequently to solve the circuit. Okay, so this circuit a little bit more difficult. So here you can see R1, R2, and R3. They are not parallel or in series. Not in parallel nor in series. Okay, so here you can see one loop, this is another loop. So you cannot just change these three resistors to be something like parallel. They are not in parallel. If they are in parallel, they should be something like this. Then this case it is parallel, but this one is not because we have the battery in between, so they are not in parallel. If I just move, for example, if I have only one battery, then we can say these two resistors are in parallel, but not for this one. Okay, so you can just change this to a parallel resistance, and then finally you can find this one and this one are in series. Okay, so you need to be careful to distinguish whether the resistors are in series or in parallel, or neither of them. Okay, so in this case, we try to solve this circuit. So we will try to use something called node analysis. Node, A-N-A-L-Y, node analysis. 节点分析. Okay, so we would try to use the current to solve the circuit. Try to use the current to solve the circuit. And in that case, because this is C, this is current, so we use the current to solve the circuit. But in that case, we will try to assume some voltage. Is the other way around. Assume some voltage, which means that usually for a complicated circuit, we can freely determine one is the ground. Just say this is the ground for simplicity. Maybe you don't like this, maybe you can determine this one is the ground. It is still okay, but you can only define one node to be the ground. So let's say we define this node to be the ground, which means that this is 0 volt, and then you need to determine the others. So let's say we need to assume the voltage at this node, which say we call it VB because this node is called B. So we call the voltage. The voltage at this node is VB, and maybe you may consider whether we should name it as VA, name it as VZ. In this case, we don't actually need to. Of course, you can, but you don't need to, because if you just introduce too much variable, you will feel confused how to write so many independent equations to solve all the variable. Because if you have one unknown variable, then you need one equation. If you have 3 unknown variables, you need 3 equations. So you need to write 3 independent equation if you have 3 variables. And if you are not so familiar with it, you will feel like it's difficult to write 3 independent equations. Then feel like you cannot. Then finally you will fail to solve all the variables. So in this case, this is a special condition. It's like here we have 2 battery. This is E1. This is E2. So if we know this is VB, we can quickly know that this node should be VB plus E1. And similarly for this one, it should be VB plus E2. And of course, E1 and E2 are known variable, so that in that case, we only have one variable because they are quite dependent to each other. So we don't really need to define 3 variables. Okay, so in that case, we can try to write out the KCL, the Kirchhoff current law. So as much as we only have one variable, we only need one node equation. So of course, we define the voltage here. So in that case, we try to calculate the current I1, I2, and I3. So maybe you can just ignore this one, because you can feel like, this is entering, this is going out. So if you still use I2 as the figure light, then you should have I1 plus I3 equals I2. But I don't really like it. My habit is like, I just used to define all the current going out or all the current going in. Then you will have less chance to make mistake. You will have less chance to make mistakes, because we only need to consider current going out. If it is really going in, then this current will be a negative number. So in that case, let's try to calculate I1. Okay, so to calculate the I1 here is tricky. So here we have a battery. So you don't try to ignore this one, as much as we already know the voltage at this node. So, and also we know the voltage at this node because this is 0. This is also 0, 0. So this is 0. which means that across this resistor, we already know the voltage at node A and also at this node D, which means that I1 is nothing but a VB plus E1 minus 0, and then over R1, which means that this is I1, and then plus I2 plus I3 is 0. So for I2, we already know the voltage as is known. So the current I2 here should be VB plus E2 over R2, and then plus this one. This is VB, this is 0. So I3 is VB minus 0 over R3, like this. If you were to make I2 from bottom to top, then it will feel like this term is on the right side with a negative sign. It will still give you the same result, but generally I get used to assuming all the current going out, then yeah, you feel like all the things are positive. Okay, so and then you can try to collect the terms. So we have VB and then 1 over R1 plus 1 over R2 plus 1 over R3, which is actually this term, and this term. Okay, and then equals negative E1 over R1 plus E2 over R2. So this is the remaining two terms, this one and this one, putting on the right side. So finally, VB will be negative E1 over R1 plus E2 over R2, or over 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so as much as we don't know the value of R1, R2, R3, and E1, E2, so this is the closed form solution for VB. And as much as if we know the voltage VB, you can determine all the current or voltage at any node easily. So that's why we call it node analysis, which means that we try to use the KCL. The KCL is about the current. But for the KCL, we need to assume one or some of the voltages. So for some of the circuit, you only need to define one, because probably you can see there are 1, 2, 3, 4 nodes. So one of the node is 0, which is the ground. And in that case, you may be able to need 3 variables. But as much as these 2 variables has a battery in between, so you can quickly determine that this VA should be VB plus E1, and then this VC should be VB plus E2. So you don't need to explicitly assume VA and VC. Then you only need one variable, and then you only need one run equation. So you only choose this node and then determine all the current going out. So for the same circuit, you can also use the KVL related theory, which is called the mesh analysis, which may be a bit difficult for you, but just show you what is going on here. Actually, this method will still give you the same result, but maybe difficult for you to understand. Okay, still we just ignore this current. We just ignore this current. We can see here we have 2 loops, one loop on the left side, one loop on the right side. So we try to assume the current is something like this. This is I1, this is I2. Both are clockwise. Maybe you can ask whether it is counterclockwise. Yeah, of course you can, but you need to be careful about the polarity of each variable. Okay, so here, for this loop, we use the KVL. So KVL is like, we need to determine the voltage across a loop, and then the sum should be 0. So we need to define some current. So this is so-called the mesh current. So I1, I2 here are called mesh current. Mesh current. Okay. So you see, okay. So for example, for this mesh, for the I1, okay, it goes through one resistor, one battery, and another resistor. Okay. So let's consider this loop. So for this loop, we have mesh 1. Okay, so here, let's try to determine, this is the positive side. So we start from here. And then this current is like this. So here, this should be positive, this should be negative. In this case, we should have I1, R1, because only R1 go through this, I1 go through this resistor R1. And then here, this is positive, this is negative, which has the same direction as this one. So we have plus E1. And then for E3, it's just a bit more complicated to understand, but I would say this one, of course, I1 go through this resistor R3. And here, I2 also going through this resistor R3. And in opposite direction, which means that the total current going through this R3 should be I1 minus I2. This is the current going through the resistor R3. And as much as this is positive, this is negative. So we also hope this is positive, this is negative. Which means that I1 is the positive current, I2 is the negative current for this resistor R3. So we should have I1 minus I2 times R3 and then equals 0 because it's go back to the same loop. We can also define this one is the ground of the circuit. And then for mesh 2, okay, here, here we consider mesh 2 to be like this. So this current should be I2 minus I1 instead. So we should have I2 minus I1 times R3 and then plus. So this time we have, this is plus, this is minus. And then in that case, this is I2 minus I1. And then this is negative, this is plus. So we should subtract E2. And then this is plus, this is minus, and this is I2. So we should have plus I2 R2. I2 R2 equals 0. Something like this. And then of course, if you try to solve this joint equation, because here we have two variables, I1 and I2. Two variable I1 and I2. Okay, with two equations. They are independent. And then you can really solve I1 and I2 out. In fact, you can also solve the circuit. So this is how the mesh analysis work. But yeah, as most of you are not ECE students, and so I suppose if you can really understand this method, the node analysis would be good enough. Okay. So here we talk about the multi-loop circuit, which is like here we have a battery. Here we have one R1, R2, R3 in parallel. So we can have the parallel equivalent resistance, which is like we take the reciprocal of the resistance, add them together, and then take the reciprocal again. So it's the parallel resistance. Okay, so this is nothing special. But compared with the capacitor, here, if we have resistor in series, we add them together. And then if we have capacitor in series, we take the reciprocal, sum them up, and then take the reciprocal again to be the series capacitance. But for the parallel resistance, we should take reciprocal and then take the sum and then take the reciprocal again for the parallel resistance. And for the parallel capacitance, we just need to add them together. Okay, so here we haven't talked about the inductance. So inductance will be on the left side. Inductance will be on the left side. If we have series inductance, then L equivalent will be summation of Lj, j equals 1 to n. And then if we have parallel inductance, it should be 1 over L equivalent equals summation of 1 over Lj. Ljj from 1 to n. So yeah, so for the resistance and inductance, in terms of parallel or series, they are similar. But for the capacitance, they are not the same. And you may be able to understand it later when we talk about the phasor. In chapter 31, we will talk about something called phasor. Maybe in high school physics, you have learned something about that. You just express something called the impedance. Impedance is like the resistance plus J times omega L minus 1 over omega C. 1 over omega C. So the resistance is a real number. The impedance of an inductor is like an imaginary number, and so as the capacitance. So it's like CR is like nothing but the R. And then for the CL, it is like J omega L. And then for impedance of a capacitor, it is like 1 over J omega C. Okay, in chapter 31, we will talk about this part. Okay, so here we have another sample problem. Okay, so this one. Okay, so here, the figure A shows a multi-loop circuit containing 1 ideal battery and 4 resistance. So here you can see this is the battery, and then here we can see through 4 resistors from R1 to R4. So here, as much as here we only have 1 battery, and then you can expect that finally all these 4 resistors can be simplified to be 1. Can be simplified to be 1. But you need to be careful about how to simplify it, rather than just see, we just add them together, or just all of them are parallel. Not that easy. Okay, so you need to have some simple observation. So we can see B and C. So in between we have R2 and R3. We can clearly see that R2 and R3 are in parallel, because these two nodes are directly connected together. These two nodes are also directly connected together. So R equivalent should contain one term is like R2 parallel with R3. Okay, so maybe we just change the circuit to be something like this. This is R1, this is R2 parallel R3, and then this is R4. Something like this. Actually, I don't need to do so, because when I see it, I can directly see the result. But maybe you are new to this, so I just draw this out, making you feel like comfortable. So this is E. Okay, so replacing R2 and R3 in parallel to be this equivalent resistance. And then finally, this circuit is like this, which was single loop. So in a single loop, okay, these 3 resistors are connected back to back, which means that they are in series. So we just need to add them together. So we have R1 plus R2 parallel with R3, and then plus R4. Okay, so we just need to substitute the number. We have this is 20 plus 20 parallel 12. Sorry, not 12. This is 30, and then plus 8. Okay, so this is 20 plus 20 parallel 30 is 20 times 30 all over 20 plus 30 plus 8. Okay, so this is 600 over 50, which is 12. So we have a 20 plus 12 plus 8, which is 30. 30 ohm. Okay, so in that case, what is the current through the battery? So it is simple, which is I equals E over R equivalent. E is 12 volt over 30. So this is 0.48. Okay, this is the answer to question A. Sorry, this should be 40 instead of 30. This is 20, this is 20, this is 40. Okay, so this is 40, and then the answer should be 0.3 rather than 0.4. Okay, sorry. Yeah. Okay, so for part B, what is the current I2? I2 means the current going through R2. So this is I2. And in the previous page, we know I is 0.3. This is I equals 0.38. This is I equals 0.38. Okay, for me, it is so-called the current divider. So I usually will remember a equation like I2 equals R2 plus R3, and then here we have R3, which is nothing but and then times I, because this is I and then going through two paths. So part of the current will going through R2, part of the current will going through R3, and then the ratio is like this. So this is the sum of them, and then in the denominator and the numerator will be the other resistor. So this is nothing but 30 over 20 plus 30 times 0.3. Okay, so this is 0.6 times 0.3, which is 0.18. Okay, maybe you feel like this is why this is true, and actually yeah, maybe I can go through it slowly. So it is like you can actually determine the voltage between node B and node C, which is VBC is I times R2 parallel R3, because just now we have the circuit like this. Okay, this is R1, this is R2 parallel R3, and then this is R4. This is R4. Okay, so this is node B, this is node C here. Okay, so the voltage VBC here should be like I times R2 parallel R3, which is 0.3 times 12. 12 is 20 times 30 over 20 plus 30. So this is 12 times this one is 3.6 volt. And then you can determine I2, because you know VBC is 3.6. So I2 should be VBC over R2. Okay, so in that case, it is 3.6 over R2 is 20. So this is 0.188. So okay, so if you don't put in all the number, and then you can see this is R2 over R2 times R3 over R2 plus R3. And then finally you can see this R2 cancel with that R2. So finally it will be this factor. And then similarly, I3 is nothing but R2 over R2 plus R3 times I. So it is 30 over 50 times, sorry, this is 20, and then 0.3, so which is 0.128. Or maybe you can just subtract 0.3 by 0.18, which is 0.12. Okay, so let me talk about this one first before we have a break. Okay, so here it says the figure shows a circuit whose elements have the following values: E1, E2, R1, R2. So R1, R1, R2, R1, R1. And then here we have E1, E2. Also, this one is E2. So it is not possible to simplify the circuit because none of them are in parallel or in series. And actually asks you the current in each of the three branches, which means I1, I2, I3. Okay, so here we can actually determine this is I1. We can use the mesh analysis. Of course, you can still use the node analysis because, yeah, for the same circuit, you can either use a node analysis or mesh analysis, but try to avoid using both together. Using both together will make you feel confused on how to write so much independent equation to solve all the variables. So here, let's try, this is I1, this is I2, because this is I2 pointing to the left side, this is I1 pointing to the right side. So let's try to assume the mesh like this direction. Okay, for the mesh one, let us start from this node. Okay, so we go this way. So the first one is E1. E1 is like going up. E1 is like going up. Okay. So E1 equals, and this is going down. This is going down. So this is positive. This is negative. Maybe you can just put it on the other side, and then it has a negative sign. But as much as the current is in this direction, this is from negative to positive, will be a negative number. So we put on the other side of the equal sign. And then here we have I1, R1. I1, R1. And then here we have I1 plus I2. So here it should be I1 plus I2. So we have a I1 plus I2 multiplied by R2, this resistor. And then this is going down. This is going down, so we have a plus E2. And then for here, we have another I1, R1. So this is the first mesh equation. And then for the second mesh equation, let us start from here. So we can see this is E2. This is E2. This is another E2. Yeah, this is E2. So maybe we can start from here. So this is E2 going down. So we have a E2 this way. Okay, so we go to here. So we have a E2 here, and then I1, R1, I2, R1, which correspond to this one. And then go to here, I1 plus I2 times R2, plus I1 plus I2 plus, and times R2. And then this is also going down, so we have a plus E2, and then going back to here. This should be a plus I2, R1, plus I2, R1. Okay, so actually we can just simplify these two equations. This is the first one. So the first one will become, okay, so we move this over. we have E1 minus E2 on the left side, and then we can simplify. We have I1 R1, I1 R2, and then I1 R1. So altogether we have 2R1 plus R2, and then times I1. And then for I2, we have this one R2 and nothing else. So we have R2, I1. And then for the equation 2, E2 and E2 will cancel each other. So we only have 0 on the left side. And then this is this is I2. So we have, this is I1, R2. And then, okay, so this should be R1 rather than I1. This is R1. Okay, so we only have this I1 on the right side, which means that we have R2, I1, and then plus. This is I2, and also I2. So we altogether have 2R1 plus R2 multiplied by I2. Okay, so in that case, we have two unknown variables, I1 and I2, and two equations. So we can be able to solve I1 and I2 out. Okay, actually we can just plug in the number. E1 is 3 minus 6 equals, this is 2 times 2 plus 4, and then I1 plus 4 I2, and then the next one is 0 equals R2 is 4 I1 plus here is still 2 times 2 plus 4 I2. Okay, so in that case, we have 8 I1 plus 4 I2 equals negative 3, and then 4 I1 plus 8 I2 equals 0. Okay, so in that case, I1 equals negative 0.58, and then I2 equals 0.258. Okay, so here we already know I1 and I2, and then I3 will be nothing but I1 plus I2. So I3 is I1 plus I2, which is negative 0.5 plus 0.25, which is negative 0.258, which means that the I3 should be from bottom to top. The amplitude will be 0.258. But here, of course, in the figure, it defines from top to bottom, so it is negative 258. Okay, so let's have a 10 minutes break.